Hey, welcome everybody. Today we have an extra special event for you all as we will be talking to two experts, Dr. Kevin Henke and Dr. Gary Loechelt, who will be joining us shortly about young Earth creationist claims dealing with helium diffusion rates in zircons. The claim is that the helium diffusion rates indicate that the Earth is young, and both of these gentlemen have written extensively about this topic and whose papers can be found at Talk Origins about it. This will be part one of a two-part series with a presentation given by Dr. Henke, followed next week by a presentation given by Dr. Loechelt. But before we start, let me give a kind of a brief overview of my guest and the topics we'll be discussing today. Dr. Kevin Henke has a PhD from University of North Dakota with a postdoc appointments at North Dakota State University and the University of Kentucky, with his expertise being in mineralogy and geochemistry. Dr. Gary Loechelt has a PhD in Science and Engineering of Materials from Arizona State University, and he specializes in semiconductor electronics and works extensively with diffusion rates. They both will be giving a refutation to the rate project findings, specifically to an article published in Creationist Journal entitled Helium Diffusion Rates Support Accelerated Nuclear Decay by Russell Humphreys, and also co-authored by Dr. Stephen Austin, Dr. John Baumgartner, and Dr. Andrew Stelling. Dr. Humphreys has graciously agreed to watch these presentations and provide his counterpoints to them, which will be uploaded to the Great Debate Community webpage at www.greatdebatecommunity.com, while Dr. Baumgartner has declined to do so, and I was unable to reach Dr. Austin and Dr. Snelling, but they are more than welcome to provide their rebuttals if they should ever watch these videos. And I want to make it clear that we will be only concerning ourselves with the science involved in this topic and not the theological claims made by creationists. This video is not to attack or denigrate anyone's personal religious beliefs or convictions, and we will be strictly addressing the scientific claims made by young Earth creationists from the Rate Project. This topic is not an easy one. It does require a little prerequisite knowledge of some geology, nuclear physics, and maths, but I don't wish that to dissuade people from joining in on the discussion. So please take notes. And if you have any questions, we will try to have a short Q&A after Dr. Henke's presentation, and possibly even a separate after show where we can have people join us to ask questions directly to my guest. Dr. Henke, would you like to please introduce yourself and we can get right into your presentation?
Thank you very much. Do you hear me okay?
We hear you excellently.
Okay, good. First of all, I want to say greet everybody and say hello, and I also want to greet Dr. Humphreys. Certainly, I disagree with him on many points, but I have no animosity against him, and I wish him well in 2018, and I hope he enjoys his retirement. The title of my talk is Helium Diffusion in Zircons, Some Comments on the Claims of Young Earth Creationist Dr. D. Russell Humphreys. Oops, just here, and let me go to, excuse me here. All right, make sure, okay. The highlights of this talk are from my talk origin essay, and it was last updated in 2010, and you can certainly consult it for more details. I'm not going to go into great detail on any of these issues. It has at least 11 peer reviewers, and this is important because Dr. Humphreys has accused others in me of avoiding peer review. But our peer reviewers included individuals with strong backgrounds in chemistry, physics, and material science. And they actually are quite familiar, or some of the peer reviewers are actually quite familiar with this topic. My 2010 update of my talk origin essay does respond to criticisms of my earlier versions of this essay in Dr. Humphreys' papers from 2005A, 2006, 2008A, 2008B, and 2010. Dr. Humphreys posted a note on January 6, 2018 on the Great Debate Community website indicating that I had not responded to him in 11 years or since 2006. And that is not true. My talk origin essay has responded to him. And then after 2010, I let Dr. Loechelt take the lead on the discussions here. There are many unanswered questions about Dr. Humphreys' work, and I've listed in Appendix C of my talk origins essay a list of of very important questions that Dr. Humphreys has not answered. Okay, so Dr. Humphreys and also creationist Mr. Gentry's samples came from some rock cores that were collected from the subsurface. They're Precambrian, and they were collected in 1970s and early 1980s to a depth of 4.3 kilometers. The samples are from Fenton Hill, New Mexico, and were part of a geothermal study to determine if the hot rocks in the subsurface could be used to generate geothermal power. Dr. Humphreys and his colleagues did this study as part of their RATE project, which is an effort to demonstrate that the Earth is only 6,000 years old by doing experiments and also uh, by reviewing the literature. Zircons are zirconium, hafnium, silicate, and also biotites were sampled. Now, zircons are very common in metamorphic igneous rocks and even sedimentary rocks, but they're almost always microscopic. They're also very robust minerals. They have very high melting points, and they do not dissolve in water at ambient temperatures. Young Earth creationist Dr. John Baumgartner collected the samples for Dr. Humphreys. So Dr. Humphreys and his team performed helium diffusion studies on the zircons and biotite. He concluded that the zircons are only 6,000 plus or minus 2,000 years old. This is one standard deviation using the biased standard deviation equation. Now, this coincides with the young Earth biblical view of a 6 to 10,000 years old Earth. However, when I entered the best available data, this is from Gentry's second 1982 article, and Zartan in 1979, into Dr. Humphrey's equations, I got highly inconsistent dates that ranged from 200 to 1.7 million years. And the best available data do not yield a date of 6,000 plus or minus 2,000 years, but I got a ridiculous result of 90,000 plus or minus 500,000 years. This is two standard deviations. And there's something really wrong going on here with, I think, Dr. Humphrey's equations when you get to the standard deviation larger than the age. And you can see my calculations in detail in my talk origins essay. Now, shown by Dr. Loechelt's more thorough modeling efforts, Dr. Humphrey's starting assumptions, equations, and data are definitely seriously flawed. The lead dates of the zircons are about 1.4 billion years old, and this is from Appendix A of Dr. Humphreys and others' 2003A paper. And these are consistent with Dr. Loechelt's old Earth model. The first thing I want to talk about is Dr. Humphrey's misinterpretation, or maybe I should call it manipulation, of helium diffusion data in a Russian paper by Megomendov, 1970. Now, Megomendov measured the helium and the lead diffusion in zircons and obtained activation energies. The activation energy is the minimum amount of energy needed for a chemical reaction or for diffusion to occur. And this is the graph from Megomendov here. It's rather messy, so I redrew it and cleaned it up a little bit. Now, Megomendov lists the activation energy for helium in his Russian zircons as 15 kilocalories per mole. This is determined from the slope of the intrinsic curve shown in red in the graph. Megomendov's diffusion data were 5 orders of magnitude higher than the data from Humphreys et al., and also from another paper by Reiners et al. 2002. Now, using Dr. Humphreys' dating equations, back in 2000, Dr. Humphreys, and then also in 2004, young Earth creationist Armitage, claimed that the ages of these Ural Mountain zircons would only be a few decades to centuries. In other words, Dr. Humphreys used his dating equations and said these zircons would be about 22 years old. Now, everybody agrees this is not possible. The zircons have a lot of radiation damage, and so they're very old. The zircons are from the Ural Mountains of Russia, and the Ural Mountains are about 250 to 300 million years old. Now, instead of questioning his dating equations and methods, Dr. Humphreys assumed that the natural log diffusion data on the Megomendov graph must be incorrect, and that the units should be in log base 10. You see here, this is on from Megomendov's graph. He uses Ln, and then D is the diffusion, and sigma here is electronegativity. or excuse me, electrical conductivity. But why should these Russian Ural Mountain zircons have the same diffusion values and activation energies as American samples? The huge differences in diffusion between the American and Russian zircons are not surprising. The Russian zircons had a lot of radiation damage. So Dr. Humphrey's misinterpretation of Megamendov's graph leads to some blatant inconsistencies. Humphreys back in 2000 admits that the activation energy of 15 kilocalories per mole is only taken from the slope of the intrinsic curve in red on the upper left. 15 kilocalories per mole is consistent with the orientation of the curve on this graph. I took a photocopy of this curve because Megamendov did not publish his Helium results in a table. And so I tried to estimate the slope, and it came out to about 16 to 17. So it's close to 15, considering that there would be drafting errors and measuring points off of a photocopy of a graph. Yet Dr. Humphreys obviously failed to realize that his log base 10 misinterpretation would change the slope of the intrinsic curve so that the activation energy would then have an unrealistic value of about 40 kilocalories per mole, shown here in the green. You can see that the green slope is definitely steeper than the red. Now, we know from a footnote in Dr. Humphrey's 2003 A paper that he had an English translation of the Russian article. The date, equations, and other statements in Megamendov's article clearly indicate that natural logs were used, and Dr. Humphreys has no justification for changing the results to support his agenda. We first of all look at Megamendov's equation 4. It has exp here. This is e to the x, or inverse natural log, and not inverse log base 10. Surprisingly, this equation appears in Dr. Humphrey's paper, 2003 A paper, so he should know that this is indeed inverse natural log. If Megamendov and others had wanted to use log base 10, they would have had to insert this conversion factor into the equation, like what was done in McDougall and Harris in 1999, page 144. You need this conversion factor. Also, Megamendov's equation 5 uses natural log. And we can demonstrate this. I do this in my talk origin paper. I go through and I derive Megamendov's equation 5 from 4. Again, natural logs are necessary. So here are the steps, just briefly. And you get to the point where you have to divide both sides by natural logs. And again, if you want to use log base 10, you have to insert a conversion factor into this formula for it to work. Now, although Megamendov only listed his helium diffusion results on a graph, his lead results are listed in both a table, shown here, and a graph. So we can then determine whether Megamendov used natural or log base 10 or base 10 logs by entering his lead diffusion results from his table into equation 5, and we'll see if we obtain an activation energy of 58 kilocalories per mole for lead, as indicated in both his English abstract and his original Russian paper. We have no reason to believe that Megamendov used Ln to represent log base 10 in his graph, but then he used Ln to represent natural logs in his text and equations. And when we do this, we find, lo and behold, using natural log, we get the exactly correct value, 58 kilocalories per mole. If we use log base 10, we get the incorrect value because we don't use the conversion factor. So there's no doubt that Megamendov used natural logs. This means there's something wrong with Dr. Humphrey's dating equations if they indicate that these zircons are only about 22 years old. That is from 1950. They were supposedly formed about 1948. That's just not possible. Now, Creation Wiki basically will do anything to defend Dr. Humphreys. So they ignore the log-based equations and data in Megamendov 1970. And what they do is they try to obtain an activation energy of 15 kilocalories per mole on a log base 10 graph by just simply taking point number 3 and point number 7 and connecting it with this dotted line. And lo and behold, they get activation energy of 15. But again, this is not supported from what Dr. Humphreys has said back in 2000. Dr. Humphrey says that the intrinsic curve should be along this red line, which happens to be in this format about 40 kilocalories per mole. And another problem is that if, let's say that we want to do a least squares fit on all of the data points, if we do that, we come up with a value of about 20 kilocalories per mole and not 15. And so I think it's obvious that Megamendov was using natural log and only working on the intrinsic curve. Now, Dr. Humphreys also has a different view of the Precambrian geology of the Fitton Hill cores. He thinks that the cores came from one giant layer of granodiorite, which he named the Hemez granodiorite. In this diagram, we can see Dr. Humphreys' samples in red, and then Gentry and others from his 2 papers in 1982 samples are shown here in blue. Now, Dr. Humphreys admits that, and I'll read this, measurements of noble gas diffusion in a given type of naturally occurring mineral often show significant differences from site to site caused by variations in composition. And that's exactly what we saw between the American and the Russian zircons. Continuing. For that reason, it is important to get helium diffusion data on zircon and biotite from the same rock unit, the Hemez granodiorite, which was the source of Gentry's samples. Now, Dr. Humphreys and his colleagues correctly recognize that it's important to know the number, types, and origins of the source rocks of their samples. However, their conclusions are wrong. Based on information in Humphreys' 2005 article, I emailed Dr. Baumgartner to find out more about the samples that he collected for Dr. Humphreys and the origins of the mysterious Hemez granodiorite. And Dr. Baumgartner gave some very gracious replies in his emails. He really was very kind. In my private emails with Dr. Baumgartner, there's no evidence that he used microscopy, X-ray diffraction, and other analytical methods to identify the rocks or minerals. I specifically asked him for that information. He didn't provide it. Dr. Baumgartner's conclusions appear entirely based on unreliable naked eye observations, including assuming that orthoclase potassium feldspar is always pink. In other words, he described distinguishing between the so-called granites and granodiorites by looking at the number of pink grains and assuming that they were orthoclase. The problem is that orthoclase may be white, clear, gray, and in rare circumstances, yellow and green. And other minerals found in igneous and metamorphic rocks may be pink, such as quartz or calcite. Dr. Baumgartner claims that the vast majority of the cores are granodiorite. This is incorrect. Laughlin, in 2 papers in 1981 and in 1983, say no. According to Laughlin, they're about 75% gneiss. And Gentry et al., 1982a, recognizes that some of their zircons indeed came from gneisses. So here's a granodiorite. It's an igneous, intrusive igneous rock. Over here is a gneiss, a metamorphic rock. Igneous rocks form from melts. Metamorphic rocks do not. By definition, a metamorphic rock forms in a solid state, even though they may look similar. This is what I think happened with the rock misidentification. Dr. Baumgartner mentions collecting granodiorite and avoiding the dark gneissic veins. Actually, they should be called foliation or layers. Now, by definition, if dark gneissic veins, or actually layers, are present, then associated light-colored gneissic layers must also be present. You can't have one without the other. The evidence indicates that Dr. Baumgartner misidentified the light-colored gneissic layers as granodiorite. Now, according to a report by Dr. Todd Freely in April 2007, he says that Dr. Baumgartner now admits that Dr. Humphrey's zircons came from gneisses. Dr. Freely went to a rate presentation in Montana. From the back of the room, he and his students could tell that the slides were of gneisses and not igneous rocks. And then he talked to Dr. Humphreys and Dr. Baumgartner afterwards, and that's when, according to Dr. Freely, Dr. Baumgartner admitted that the samples are indeed gneisses. Now let's look at the rock cycle. calling an igneous rock a metamorphic rock or a metamorphic rock an igneous rock is like calling a frog a reptile. It's just inappropriate. Again, metamorphic rocks form in a solid state. Now, gneisses, according to field and laboratory studies, form at temperatures of about 600 to 750 degrees, but at extremely high pressures of 4,000 to 6,000 bars. Atmospheric pressure at sea level at 25 degrees Celsius is about 1 bar. So this is 4,000 to 6,000 atmospheric pressures. No melting is involved. And so these would be depths of about 15 to 22 kilometers down. That means that the gneisses at Fenton Hill have been uplifted from where they originated. And if you get water present, and depending upon the rock chemistry, you can get melting of rocks at 650 to 1,000 degrees Celsius. When a rock will begin to partially melt by the melting of the quartz grains, and it forms what is called a migmatite. A migmatite is a mixed rock. It's partially igneous and partially metamorphic. That is, the part that never melted is metamorphic, and the part that melted and then recrystallized is igneous. So you end up with magma, and then the magma cools to granodiorite or granites. There are two major types of gneisses. Orthogneiss form from metamorphosed igneous rocks. Paragneiss forms from metamorphosed sedimentary rocks. Sometimes we can distinguish by chemistry and mineralogy an orthogneiss from a paragneiss, especially if we look at the aluminum chemistry and the aluminum minerals. Now, orthogneisses, again, form from igneous rocks, and so they're going to contain some zircons that will survive metamorphism. The metamorphism may also produce other types of zircons or recrystallize the zircons. Also, the magma that forms and that would eventually crystallize into the parent igneous rock may pick up some surrounding zircons in them. Now, paragneisses form from sediments, and so they may contain even a greater variety of zircons. As an example, right now we have sediments piling up in the Gulf of Mexico. Some of these sediments are now buried so deeply they're beginning to undergo diagenesis. They're beginning to turn from sediments into sedimentary rocks. And so here in the Mississippi River, we have zircons weathering out of the Rocky Mountains, going down through the Missouri River and some other tributaries into the Mississippi River. We can also have different types of zircons weathering out of the Appalachians and going down the Mississippi River from the Ohio River. And then the headwaters of the Mississippi are located in Minnesota. And some of these rocks are the oldest in North America. They're about 3.5 billion years old. So we're going to get different types of zircons piling up in sediments that can eventually form paragneisses. And because these zircons have different sizes, shapes, and amounts of uranium and thorium, they are going to affect Dr. Humphrey's dating equations. And he needs to thoroughly sample his zircons to make sure that they're not of different origins. So again, we look at the geology of Mr. Gentry and Dr. Humphrey's zircons. Dr. Humphrey's zircons are labeled samples are 2002 and 2003. They are from gneisses. Mr. Gentry's zircons for his samples 1 and 2 are also from gneisses. Mr. Gentry's samples 3, 4, 5, and 6, some of them do come from either granodiorites or could come from monzogranites. So the geology of the Fenton Hill cores is quite complex. Now, Creation Wiki defends, again, Dr. Humphrey's mistaken geology. They argue that Gentry's sample 1 came from a granodiorite, and Dr. Humphrey's samples were from a granite. The referencing in this website is terrible, but the claims appear to be based on an outdated reference, Perdaman et al. 1974. Their other geology reference, Laney, 1981, identifies the rocks as indeed being gneisses. Perdaman only had drill cuttings to rely on, which are hard to identify, rock fragments. Later and more thorough investigations with far more complete core samples indicate that these zircons came from gneisses, and this would be Laughlin and Laney and other articles. Creation Wiki also argues that granodiorites have compositions close enough to granites to be called granites, and this is just sloppy and unacceptable and has nothing to do with gneiss. This is like calling a chimpanzee a gorilla. Igneous rocks are well defined by mineralogy and chemistry, but this requires detailed analyses and not naked eye observations. Here's an example of an identification diagram based on mineralogy to distinguish a granite from granodiorite. The Jemez granodiorite is Dr. Humphrey's unauthorized and inaccurate nomenclature. Humphreys admits that he invented the term Jemez granodiorite to describe all of the Precambrian rocks in the Fenton Hill cores. Now, the U.S. Geological Survey's Geologic Names Committee and the North American Stratigraphic Code, maintained by the North American Commission on Stratigraphic Nomenclature, established rules that all scientists must follow if they want to introduce a name for a rock unit into the literature. It's totally inappropriate for Dr. Humphreys to name his own rocks and then put these unauthorized and inaccurate names into the literature, especially when most of the rocks in the Fenton Hill core are not even granodiorite. The consequences of the geology. Dr. Humphreys and Gentry, zircons.
Just let you guys know that Dr. Henke had said prior to this that he might have problems because he's having an ice storm, but I think he's just come back. So let me show him again. Welcome back, Dr. Henke. You there? You're gonna have to unmute. I guess he's having some nasty weather back there, so he might drop out every so often. Okay, while we're waiting for him, Dr. Loechelt, are you there?
Yes, can you hear me?
Yes, welcome. We had to start. I know you're running a little bit late, but thank you for joining us. Do you really want to really quick give a brief description of this subject and your?
Can you hear me now?
Oh wait, there we go. Yes, Dr. Henke.
Okay. Yes. When did you cut out? Or when did you cut out?
You were at the point in you're saying
Consequences of the geology errors.
Yeah.
Okay, I'll
Go back to the consequences.
Okay, we'll get to the consequences here. Yeah, we're having ice storms here. It's doing some crazy things. Okay, let me check to make sure that's.
And you're going to have to represent your presentation.
Yeah, just a second here.
And I'm boosting up your volume.
Okay, now can you see and hear and everything?
I still can't see your presentation, so you need to show.
Okay, just a second.
And Dr. Loechelt, we'll get to you right after the presentation. Plus, I have quite a few questions to ask, and I think what we're going to do is kind of start with a little basic stuff because I know a lot of people in the live chat probably don't have much experience, if any, on these topics. So if I'm going to ask some very basic questions, it's just because I want people that don't have any experience with physics or especially nuclear physics to kind of still get a bit involved with this, because I know this is very technical right now and the presentation is probably going over a few people's heads, but that's fine. I want it to be just like this, and then we can always back it up a little bit and kind of get into some basics so they have an understanding of what we'll be discussing. Is that okay?
It's to your credit to take on a challenge like this, so my compliments to you.
Thank you. This is actually one of the most difficult topics that I've had to kind of learn about. It's much more difficult than the polonium halos that I've done a presentation on. It's probably the most technical because it requires so many different disciplines of science to really wrap your head around.
Okay, can you see it now?
Let me present you and see what we got here. No, I cannot. It just still shows your icon.
Okay, let me try it again.
Yeah, Steve, if it's any consolation, I had a physicist I know review the mathematics that I did for the diffusion, and this guy is an expert in general relativity. And he said it was some of the hardest math that he had worked through in quite some time.
I can imagine.
So to me, that was a compliment that a guy who's an expert in general relativity said, I could follow your math, but it was some of the hardest math that I've seen in quite a while.
Yeah, if we get started with Laplace transformations and things like that, I'm done.
Now, can you see it still?
I cannot. Dr.
Okay.
Loechelt, can you see it? I'm only seeing his icon. Let me try to represent it. You need to go to screen share and then show full screen.
Okay, maybe that's it. Just see here. Okay, I'm going to screen share. Okay, and then I press share for screen 2.
You might have to exit and re-enter. Sometimes that fixes it. Just hit F5 and I'll do it automatically for you.
Okay.
And we'll get this going. G+ has a lot of technical problems, so it's not surprising. It's the way that it's poorly designed, I think. So we'll get this going.
Yeah. Well, the other thing is this is done with very little rehearsal. It's not like a movie where you have multiple attempts and you can just take the cut you want.
Yeah, we have no B-roll for this. This is all real time.
So it's not bad.
All right, let's try this again. Want to present yourself again, Dr. Henke?
Okay, can you hear me now?
We can.
Okay. Yeah, let me go back and see if we can get this to work. Okay, can you see it?
I cannot. It's still showing your icon.
All right, let me try it again. Okay, well, we'll get this going. Okay.
Oh, I think we got something here. There we go.
All right, let me try. Well, I'm getting infinity.
That's good. No, that means you're screen sharing. So now you just need to go into your presentation.
Okay. Okay,
Yep,
now,
there we go.
okay.
Yep.
Okay, so the consequences of the geology. Dr. Humphreys and Mr. Gentry's zircons come from diverse metamorphic igneous rocks. Gentry admits that some of the samples came from gneisses. Gentry demonstrates that the sizes and the uranium and thorium concentrations and other properties of the zircons may widely vary even within individual samples from the fentanyl cores. And variations in uranium and thorium concentrations in the zircons yield diverse helium concentrations. Gentry, in his second paper, 1982, found that the uranium concentrations could vary by an order of magnitude at different locations on the same zircon. Now, variations in zircon size, shape, and degree of crystallinity contribute to variations in helium retention. And even if his dating equations are correct, if the zircons do not have uniform properties, then Dr. Humphrey's dating results are invalid. Invalid data going in and invalid dates coming out. Now here are Dr. Humphrey's dating equations, and I just want you to note that there are 4 main variables, A, B, Q, and Q0. And for these equations to work, all of the values must be accurately known. Now these equations, as Dr. Loechelt will talk about next week, are based on many invalid and questionable assumptions, such as assuming isotropic helium diffusion, overlooking variations in temperature over time, and ignoring the possibility of extraneous helium from the nearby Valles caldera contaminating the zircons. Parameter A is the effective radius of helium diffusion in zircon. The dating equations assume that the diffusion is spherical, that is, the same in all 3 dimensions. However, the zircons are prisms and not spheres, so they're going to get preferential diffusion in the zircons. The gneisses, especially if they're paragneisses, as well as the igneous rocks in the fentanyl cores, could have zircons of different sizes, shapes, and origins. The value of A would vary with the size and shape of the zircon. Now, Humphreys in 2003 defines A as 1/2 the length of the zircon. This is the same as in the Russian paper, Magomedov, 1970. However, Reiner's 2004 defines A as the average half width, which can be determined by sieving. So there's advantage of using half width because you can use sieving. The problems might occur when Dr. Humphreys compare their results with Reiner's because they defined A differently. Now, Humphreys admits that the average size of the zircons is unknown, for the first set of samples from 750 meters, sample 2002. Rather than actually measuring the zircons, Dr. Humphreys guessed that A would be about 30 microns. This is unacceptable. Improper estimates of A have caused diffusion coefficients of argon in feldspars to vary by over 7 orders of magnitude at a given temperature. And the measurements of A must be accurate for all diffusion studies. You don't want to guess the value. Now, B is the effective radius of helium diffusion in the biotite surrounding the zircon. Dr. Humphreys also improperly assumes isotropic spherical diffusion in the biotite. And biotite are minerals that look like a stack of playing cards. And so if the helium comes out of zircons within the biotite, the helium will tend to go down the biotite cleavage planes rather than across the crystals. B is also an essential parameter in dating equations 14 and 17 in Humphreys 2003A, and Dr. Humphreys' efforts to eliminate sample 6 from his dating results. In some of his response to my earlier criticisms, he indicated that B wasn't all that important, and it is for him anyway. Humphreys lists only one average value of approximately 1,000 microns for B. There's no indication of how this average was obtained. There's no list of samples and measurements, no standard deviation. Now, biotites will vary greatly in size with different metamorphic and igneous rocks, which affects the size of B. When I asked about the standard deviation, Humphreys flippantly said that all of the necessary data were in his papers and I could calculate it myself. And this is false. Entering only one value of 1,000 microns, actually an average, into an unbiased standard deviation equation with degrees of freedom in the denominator is going to lead to division by 0. Now, Dr. Humphreys improperly uses the biased equation to calculate his standard deviations. When taking a small number of samples from a large population, such as zircons in core samples, the unbiased equation with n-1 should be used. Q0 is the maximum amount of radiogenic helium that is expected to accumulate in a mineral from the radioactive decay of its uranium and thorium. A certain percentage of helium nuclei will escape from the host mineral during radioactive decay, and this loss is normally considered when calculating the Q0 values. Q refers to the actual amount of helium, presumably only radiogenic helium-4 in a mineral. Now, just a few kilometers to the south of Fenton Hill is the Fallacies caldera, where test wells have significant extraneous helium, probably including non-radiogenic helium-3 in them. People need to realize the United States is an important producer of helium gas, and some of that helium gas comes from New Mexico. Humphreys did not rule out the possibility of extraneous helium contamination of the zircons in the remote past, especially with the low helium concentrations in samples 5 and 6. Evidence of past hydrothermal alteration in the cores indicates that contamination is possible, although not definite. Extraneous helium, along with other fluids, could have fused into the zircons, especially in the voids in the metamix regions. Now, after a contamination event, the helium would disperse pretty quickly from the biotite cleavage planes, far more so than the impermeable zircons. The zircons could hold on to the helium longer. Thus, biotite may no longer contain extraneous helium, but the zircons could. And like the extraneous argon in potassium argon dating, there are methods to check for extraneous helium, such as checking the zircons for helium-3 or low uranium and thorium minerals such as quartz for helium-4. Yeks often overemphasize problems with extraneous argon in potassium argon dating, that is, younger creationists overemphasize this problem. But since they're concerned about widespread extraneous argon interfering with potassium argon dating, they should check their own samples for extraneous helium, even if its presence is unlikely. Now, there are some mysterious corrections in the helium measurements, the Q results in Gentry's work. These are the original values in Gentry's 1982 paper, his first paper. But in Dr. Humphrey's 2004 paper, the values have been reduced mostly by dividing by 10. Excuse me. By 2004, Dr. Humphreys recognized that his zircon Q values were much lower than those of Gentry 1982A. After consulting with Mr. Gentry, they both concluded that there were typographical errors in Gentry et al. 1982A. Dr. Humphreys, in consultation with Mr. Gentry, changed the numbers to comply with his results in an unannounced post-conference version of Humphreys et al. 2003A paper, and then later on in his 2004 paper. There's no indication that the original 1982 lab notes were consulted to confirm the presence of typographical errors. Statements in Humphrey's 2005A suggest that the notes were lost. If the results in Gentry's 1982A paper are questionable and the original laboratory notes are lost, then the data should have been discarded and the study redone. Now, Q to Q0 indicates the fraction of the original radiogenic helium remaining in a zircon. Dr. Humphreys needs to maintain high Q to Q0 values for his young Earth creationist model to work, that is, values around 0.58 or 58%. That is, the zircons are supposedly too young for a lot of the helium to escape. And these are the values that he wants here. After correcting the Q typos and to keep his high Q to Q0 values the same, Dr. Humphreys is forced to accept a Q0 value of only 15 nanocubic centimeters standard temperature and pressure per microgram of zircon. So how did Dr. Humphreys justify a Q0 value of only 15? Well, we don't know, because in 2005, Dr. Humphreys promised to show the necessary calculations in another paper in the Creation Research Society Quarterly, but he never did. Dr. Loechelt and I argue that Dr. Humphreys' Q-off value should be closer to 40, using the highly questionable assumptions in Gentry et al. 1982A. And Gentry should have also gotten a Q0 value of around 40. For my calculations, see Appendix A of my talk origin essay. Now, data in Gentry, his second paper in 1982, indicate that the Q0 value for some of the zircons could be as high as 800, not just 15 or 40. It's simply wrong for Gentry and Dr. Humphreys to assign only one Q value to all of the samples. The large variations in the metamorphic and igneous host rocks contribute to a huge diversity in uranium, thorium size, and other chemical and physical properties of the zircons, and this demands that each zircon should have its own Q0 value. So Q to Q0, two wrongs don't make a right. Considering the unsubstantiated claims of typographical errors in Q, and that Dr. Humphreys' inability to justify his low value of Q0, how can he claim that the Q to Q0 values were unaffected and still accurate? Humphreys' 2005A tries to argue the following, but after discussing the matter with him, R.V. Gentry, I'm inclined to think that even if he, R.V. Gentry, had an error in Q0, the error canceled out when he calculated the ratio Q to Q0, which is a crucial quantity in the analysis. So how did this magic occur? Where is the evidence for the claim that the Q to Q0 values would be unaffected? How is that mathematically likely? Now, data in Gentry's, again, et al. Paper, the second paper, indicate that the Q to Q0 value for sample 1, for example, may be as low as 0.011 rather than 0.58. In other words, perhaps only around 1% of the original helium is still in these zircons rather than 58%. You can see my calculations in Appendix B of my talk origin essay. So there's a lot of uncertainty about the Q to Q0 values. Lastly, pressure is important in helium diffusion. Dunai and Roseleaf use garnets, another type of hard nesosilicate like zircons, to study the diffusion of helium in these minerals. Their laboratory studies use very high pressures, up to 250 bars. Now, the Fenton Hill samples are located between 750 and 4,310 meters deep down, or about at 200 to 1,200 bars of natural pressure. Laboratory and field studies with gneisses and their minerals indicate that the Fenton Hill gneisses would have formed at even greater depths, again 15 to 22 kilometers down at least, or 4,000 to 6,000 bars. So these gneisses formed under very, very high pressures and then came up to the surface. sometime later. Now, Donai and Roseleib concluded that under 250 bars pressure, helium would take tens to hundreds of millions of years to diffuse out of garnets, even at temperatures as high as 700 degrees Celsius. The Fenton Hill zircons were at much lower temperatures for much of their history, as what Dr. Loechelt will explain next week. Instead of using vacuum diffusion, Dr. Humphreys should have measured the diffusion at more realistic high pressures. And if he had, he probably would have recognized that these zircons are not just 6,000 years old. So in summary, the host rocks for Dr. Humphrey's samples are gneisses. He and his team totally misidentified the rocks and gave them an improper and inaccurate name, gneiss granodiorite. The Fenton Hill cores contain a variety of metamorphic and igneous rocks at different ages and origins. This affects the chemistry and physical properties of the zircons and the results from his questionable dating equations. Even Humphreys, 2003, admitted that it was important for their study for the zircons to come from only one rock unit, but they don't. The parameters entered into Dr. Humphrey's dating equations are poorly defined, questionable, or likely non-representative of the diverse geology of the Fenton Hill cores. Dr. Humphrey's misinterpretation of Mega Mindoff 1970 is totally unjustified, to the point where we could call it a manipulation or even fudging. Dr. Humphreys needs to obtain statistically representative uranium, thorium, lead, helium-3, and helium-4 measurements on numerous zircons from each rock type in the core samples. He needs to use more realistic equations with fewer assumptions, such as those used by Dr. Loechelt. Dr. Humphreys needed to perform his diffusion studies under unrealistic pressures. Now, in his 2005A and 2006 papers, he often refers to he often tries to dismiss my criticisms as a mountain of minutia or just another quibble. In other words, he tries to minimize them. However, all of my questions in Appendix C and the questions of Dr. Loechelt and many others must be thoroughly answered before his claims are worth recognizing as plausible. And I certainly hope that Dr. Humphreys will finally take my criticism seriously and not just simply try to dismiss it as being trivia. So next week, Dr. Loechelt will demonstrate who really has the better model, Dr. Humphreys here or Dr. Loechelt. And I should point out that Dr. Humphreys emphasizes how well his creation model lines up with his data. And so next week, we'll see how realistic that claim is. So here are my references. And I thank you very much for your attention. And sorry about the interruption there.
That's quite all right. Amazing presentation. Before we actually stop presenting you for a second. So before we get into some of the more technical stuff and to have Dr. Loechelt weigh in, and I'd like to welcome General Han Solo, who's also a physicist who just joined us in the middle of this. Let's kind of, like, if we can, clarify some of the basics for the people that are not that familiar with this topic. A lot of people don't even know why we're dealing with helium and how it relates to an alpha particle. So can maybe Dr. Loechelt or Dr. Henke, one of you, explain the relationship between alpha particle being emitted from uranium and thorium and how that eventually will become a helium atom?
Yeah, Steve, I can give a brief discussion. So if you start with the radioactive nuclei like uranium or thorium, its decay mode is through alpha decay. And it will emit a particle from the nucleus comprised of 2 protons and 2 neutrons. That's helium nucleus, but it wouldn't have the electrons. So that charged particle gets emitted at fairly high energy. It will pass a fair distance through matter. And eventually, it will acquire electrons, neutralize, and become a helium atom. And because it's emitted at high energy, it will, in a sense, lodge itself deep within crystal structure around it. And that's different than if you just had, let's say, subjecting helium externally where it could go in through cracks or so forth. This could, because it's emitted at high energy, it will embed itself deeply into the crystal lattice, and then it will stay there. And then the question is, how long will it stay there? And that really is the crux of the question. And that, assuming that Gentry did measure some amount of helium that really was the byproduct of alpha decay from the radioactive elements in the crystal, the question really is for this debate, how long will that helium reside in that crystal? Can it reside for only a few thousand years, or is it possible for it to be retained for a billion years, let's say? And that really is the crux of the argument. Humphreys and company, they claim that the only reasonable interpretation of the data is that it is retained for a few thousand years. Kevin and I, Dr. Henke and I, based upon our analysis and review of the data, we show quite the contrary, that there's nothing remarkable about the fact that zircon crystals can retain their intrinsic helium for very long periods of time.
So basically, the alpha particle is being ejected, and as it travels through its what's called mean free path, if I remember correctly, it starts to slow down and gets more ionized and starts it gets the two electrons that it's missing, forming a helium atom. Now that will stay in some point. That's actually the Bragg peak. It'll slow down. It'll actually ionize. It actually absorb electrons and become neutral. Now, the diffusion doesn't take place until after that, right? And when you're talking about the activation energy that Dr. Henke was talking about, that's the energy to move that helium nucleus from one portion of the crystal lattice to another, right? From one cell to another.
That's correct, because once the helium atom, or once the alpha particle comes to rest, it will neutralize, like you said, and it will reside in some state, some bound state within the crystal. And in order for it to diffuse, you have to apply energy to lift it to a more mobile state. And that, if it's a thermally activated process, which is what we're considering, then that would have what's called an activation energy. And that's just the amount of energy it takes. Sorry, what?
I was just saying that's the kinetic energy it needed based upon the Gibbs free energy.
Yes. Yes.
Okay. And the other things that we probably need to clear up, because a lot of people are kind of confused on this, the Q to Q zero ratio, the fraction, and that basically is the total number of helium atoms within the crystal as opposed to what should be calculated if there's no diffusion. Correct?
That's correct. Well, sorry.
Yeah,
you want to kind of touch on that again? The actual Q to Q zero fraction, because I think that's kind of critical, because that's what we're talking about, of what that Q to Q zero should be, and is it indicative of young Earth or an old Earth, based upon your findings versus Dr. Humphrey's findings?
Yeah, Kevin, you want to take this one?
Yeah, I have some questions about what the Q to Q zero values are. And again, I looked at Gentry's second paper from 1982 and some of his individual uranium and thorium measurements, did some calculations, and concluded that in some cases the Q to Q's, or Q0 may be as high as 800 instead of 15 or 40, which means that the actual Q to Q0 values in these zircons could be far lower than what Dr. Humphreys or Gentry thought back in 1982. And so we would have to do a lot more measurements to really figure out what the Q to Q0 values are.
Yeah. But I think Steve was asking more of the conceptual question: what does the quantity represent?
Right. What actually is the Q as opposed to the Q0?
Yeah. So it's the fraction of helium that remains. So if every helium atom that was generated from a nuclear decay stayed within the zircon crystal, your Q to Q0 would be 100%. It would say all of the helium is still contained within the zircon. Now, some has left. Some actually leaves immediately, because if the radioactive element is near the surface and it ejects the alpha particle towards the surface, then that's lost immediately. Even apart from diffusion, that's a surface loss effect. And so that will reduce the Q there. That's one of the factors that Gentry tried to account for that was not well quantified. So you lose some just due to alpha emission alone. And then what's left will further reduce because of diffusion. And then the question is, well, how much is left? And so that ratio of how much did you start with versus how much you have left is important physical quantity, because if you're going to model the diffusion, you need to know how much you started with and how much you have left. And I think what Dr. Henke is bringing out is, especially the Q0, how much you started with was very poorly quantified. So that just introduces huge uncertainties in that number. And that is the number that any kind of model is going to try and replicate. So it just, those uncertainties just propagate all the way through, no matter how you try and do it. Kevin and I, we looked at Gentry's data, and we were just scratching our heads, just thinking, this was not well quantified. And how can you even do a good quantitative study if you don't have a good estimate of how much helium was there to begin with?
Do we even know if you had a way to discern between helium-4 and non-radiogenic helium-3?
Yeah,
Yeah, they
do
could
it
do
through.
mass spectrometry.
No,
Yeah,
no.
exactly.
Did Dr. Humphreys, did he take into account
No,
that? Okay.
no. He assumed that all of the helium was radiogenic from the uranium and thorium within the mineral. And again, with the Fallacies caldera right next door spewing out all that helium, who knows?
Now, I know next week you're going to be talking a lot more about diffusion and a lot of the technical side physics involved in diffusion rates, because that's your specialty, Dr. Loechelt. But do you only want to kind of real quick explain some of the parameters involved with diffusion rates, what take into account pressure differential gradient, area, diffusion constants, and things like that, so people kind of have an understanding? There's a lot of factors that go into determining the diffusion, and your criticism seems to be that Dr. Humphreys didn't take into account a lot of these things and kind of, I hate to say, but fudge some of the numbers to fit his preconception rather than what the data indicated.
Yeah. Would it be worth, Kevin, going back to one of your slides that shows the model if we want to talk about some of that?
Yeah, let me try to bring it up.
Yeah. Well, while Dr. Henke is doing that, when you do something like this, a diffusion model, I conceptually think of it as, you look at the microscopic aspect and then sort of the macroscopic aspect. And both of those factors come into the final equation. The microscopic aspect is sort of what happens at the atomic level. The atomic level, you have a zircon crystal, and then you have a helium atom residing in that zircon crystal in some state. And
can you see my diagram?
Yes.
Yeah, I can see your presentation.
Okay. I don't know which slide you wanted.
Where you show where you show his basic model, the parameters A, B, T, and those. I mean, that has all the variables kind of in front of us, so we can talk through it. I think Steve would just like a brief primer. What do these numbers mean, even at just a conceptual level? So you had a good slide. Yes, that's the one I was thinking of. Yeah. So you have a D, a T, you have a B, and an A. And just to put all of that, and of course the Q and Q0. We talked about Q and Q0. So let's say we're good there. So let's talk about D. D, that's the diffusivity. So this is an intrinsic property of the material. It's really looking at things at the atomic level. The helium atom will be in some kind of immobile state. And as best as what recent research has shown, very likely that the damage of the alpha decay actually disrupts the crystal lattice and kind of creates little trap states or little block points, and the helium atoms will just reside there. It takes a certain amount of energy, thermal energy, to excite that helium atom, into a higher energy state that's more mobile. And once it does, then it can move. And the factor D accounts for that. And even though in this equation it's just shown as a single variable, it actually has a very strong temperature dependence. And I believe Dr. Henke showed previously the Arrhenius factor, the D, and the exponential of the energy divided by the KT. So it is a parameter that is, I call it intrinsic, which means if you have a small zircon crystal, a big zircon crystal, regardless, at the microscopic atomic level, it is a property that is, material. Okay, so that, are you going back to the Arrhenius one?
Yeah.
And,
Okay,
that's because of the
good.
crystalline structure that's involved. That makes the diffusion constant that way.
Yes, exactly. I mean, this is very fundamental to a branch of physics called statistical mechanics, which says that it's a branch of physics that relates macroscopic things we see, like helium leaving a crystal, to what's happening at a microscopic level. And what's happening at the microscopic level is that you have a certain energy that's required to lift a helium atom from a immobile state to a mobile state. And as we'll see next week when we get into it, you could actually have multiple states in the crystal and different activation energies, and that needs to be taken into account properly. But let's say, for the sake of of argument, we're talking about how to do a model. If you know the diffusivity, then you know something about how fast the atom can move over time. Dr. Henke, can you go back to that other slide that shows your full model now?
You mean
Yeah, you're almost there. That one, yes. So if you just glance through the equation, if you look where D is, it's always associated with T, and that's time. And that's very common because the units of D are centimeters squared per second. And so if you multiply it by time, you get to centimeters squared. So you get basically a geometrical factor. And dt, or actually the square root of dt, is a very important number. It's called the diffusion length. And it's a measure of, on average, if you put a whole bunch of helium into a crystal, let's say all localized into a very tight spot, and let it diffuse over time, the diffusion length would give you some estimate about roughly how far would it move. I mean, of course, it's has like an exponential factor to it. So some will go farther than others. Some will go farther than the diffusion length. Some will go shorter than the diffusion length. But that diffusion length is characteristic of the material and the time. So dt.
And that's why it's so very
if you look
critical to know what kind of rock you're dealing with, whether it be granite or diorite or gneissus. It's going to change how much helium is going to be diffused from there based upon the type of material and the isotropies in the material itself.
Well, it's a property of the material. So in as much as your material changes, this property will change. Okay. So the dt is something inherent to the material, at a microscopic level, and of course the t is just the time that it's had to move. And of course, if the temperature is changing over time, then you can't just do the simple product, because d will actually change over time and you have to do more advanced calculus stuff. But basically it's the same kind of thing. You start doing integrals now over ddt rather than just dt. But that's a basic part of the model. And once you have d times t, you get a geometrical factor. It's the diffusion length squared. And now the question is, how long would it take for atoms to start leaving the crystal? Well, the question is, how far do they have to go? And that's where these geometrical factors like the A's and the B's come in. Because now you're relating the diffusion length to a physical dimension that tells you how far does it have to go. And basically all these quantities, if you just look at it, there's some kind of ratio of, let's look at equation 16. That's a good example. A squared over 15 dt. If I just look at the numbers, it says this radius squared divided by the diffusion length squared is some ratio. And of course, if A is bigger, the fraction gets bigger, which makes sense. If my distance of travel is long compared to my diffusion length, I would expect a high ratio. If my distance of travel is small compared to the diffusion length, I would expect a small number. And that's why in a lot of these equations, even as they get more complex, you will see almost always dt divided by some geometrical factor squared.
And real quick,
And of course, to get everything right, you need to know just a quick thought. You need to know the intrinsic property of the material, and you need to know the boundary conditions. You need to know how far things have to travel, and you have to get all that right.
And those boundary conditions, those also change things like the surface area of the crystal itself. Because one of the things I was reading about, we'll get into some of the points that were made against the rate study on this, but was it not the case that you can take an approximation for a sphere of the crystal, and that will change the surface area conditions such that you have a different rate of helium diffusion because of that?
Well, and yeah, that goes back to what Dr. Henke showed earlier. How do you define A? If you're going to approximate your geometry as a sphere and your crystal is not a sphere, obviously there's some error there. But if you're going to use that approximation at all, what is the best choice? And if you follow what the literature does, the most preferred approach that I've seen that authors are using in the most recent publications is that you constrain the sphere to have the same surface to volume ratio as the actual crystal.
Okay, so as long as you maintain that similar surface to volume ratio, it should give you a good approximation.
That's the best approximation. Now, these zircons, they're tetragonal crystals, so that means they're like rectangles. One dimension is more square, the other one's longer. So usually you have so it's in the x and y direction, it's small. In the z direction, it's longer, usually by a factor 1.5, 2, even 3 or more. So if you think about let's say you don't pick the same surface to volume ratio. Dr. Henke showed one research, well, Dr. Humphreys used half the length, which actually is not a good choice because the helium atoms could diffuse sideways and get out faster than going along the length. Reiners in 2004 used the half width, which is still not the best choice, but if you do the math, it comes out a lot closer to the surface to volume ratio than the half length. So it's a much better, yeah, thank you, very good. It's a better approximation. It's still not the best approach. And you see even Reiners later on uses the surface to volume ratio. So even their methodology is refined over the years. But using the half length is just hard to fathom. Well, not only that, this is very interesting. In 2000, Humphreys used a criteria to maintain the same surface area, which is closer to using a surface to volume ratio criteria than the length. So he actually changes his criteria for defining A. Again, one of the mysteries, why does he do that? When he adopts one practice, and then in his next publication, he changes it without explaining why he's doing it differently this time.
And real quick, since we're on that, go ahead, please.
Can I just make one thought?
Yes, of course.
And this is the thing that's fascinating, because his value for A is bigger than what you would calculate using the other methods. And also he does some assumptions about the biotype, which are not accurate. If you fix those things, I get an age of 600 years, not 6,000 years. And this might be one of the reasons why he picked the half length instead of some of these other definitions of A. Because if you put in what I'd call more accurate value, he gets numbers that are less than 1,000 years old.
Which wouldn't fit his presupposition of the age of the Earth.
No, and you would have to start questioning whether Columbus discovered America or not. I mean, it has some real logical difficulties if you say that is valid. And of course, if you come up with a number like that, then you have to question the whole methodology. And I think that's what Dr. Henke is saying, is ignoring some of these unrealistically low numbers are actually a bigger crime and I'm sure I'd call it a crime, but if you ignore these situations where you come up with an unrealistically low number, that's serious, because no one would believe a 600-year-old Earth. No one would buy that. But if you tried to claim that, you'd have to question the fundamental methodology. And if by tweaking parameters, now he gets a canonical age of 6,000 years, which is more acceptable to some, why is it valid? Why would you accept that reasoning and not a 600-year-old Earth using better approximations?
Right, right. And that's some of the modeling you'll be talking about next week, correct?
Correct.
Okay. And real quick, a lot of people in our live chat do know math, and so they kind of went nuts when you started talking about this. Can you, for the folks who don't, can you explain when he was Magnomedov's formulas, and he was using instead of using expx, which is e to the x, that he somehow translated that into natural, or sorry, from natural base to log 10 base? Because I don't think anybody who's in the live feed right now that knows math sees at all how he would possibly made that mistake. So can you kind of explain how critical that really is?
Is that addressed to me or Dr. Henke? Sorry.
Either or. Dr. Henke, do you want to take this one since it was on your presentation?
Well, I can't really explain why he came up with log base 10, because the equation is natural log, and he listed the equation in his own papers, and it would have natural log in it. But if we start out with Magomedov's equation 4, which is common, again, Dr. Humphreys uses this equation, a lot of people use it, and go to his equation 5, you come to the point where you have to divide natural log on both sides of the equation. And if you're going to use log base 10, you have to put in the conversion factor into it. But with the equation 5 is dealing with two diffusivities, and that's why you how you go from equation 4 to 5. I don't know if that answers your question.
It does. But the original Russian was clearly using natural logarithm.
Oh, sure.
Okay.
Sure.
Yeah.
And again,
So,
that's common. That's again, if you want to use log base 10, you got to put in that conversion factor, like they did in McDougall and Harrison. But Creation Wiki seems to be forgetting about this conversion factor when they use the equation, and so I don't quite know the justifications for it, but it's just wrong.
well, something to note, and this is just an observation, but there's documentary evidence to prove what I'm about to say, is that Humphreys has a history of changing equations, data in tables, and things like that to support his conclusion if he discovers sometime down the road the original interpretation didn't support his conclusion. And I've seen this. And so I think there was a real temptation, perhaps on his part, to interpret Magomedov in a way that would be supportive of his conclusion, rather than saying these zircons are metamic, they're so radiation damaged that we just can't compare them. He was looking for supporting evidence, and he found a way to create supporting evidence by reinterpreting the equations when there was no basis for doing that. And it's not the first time that he has changed his justification for an argument rather than questioning the conclusions that he based upon an argument that was incorrect.
Yeah, he also does it with Gentry as well. Gentry's 1982 first paper changes the numbers. But you see, when you end up having equations that say that these Russian zircons are 22 years old, there's something very, very wrong there. And I think instead of first questioning his own mythology and equations, which is the normal way, he basically blamed Magomedov and said, well, there must be, Magomedov must have plotted something wrong on his graph. And it turns out Magomedov plotted the data correctly. And so now we know Dr. Humphreys has to explain his equations and why they would give ridiculous ages for these Russian zircons.
And since you brought it up about the radiation damage in these crystal lattices, can you briefly kind of describe how because these rocks have a lot of radiation in them and it does cause damage to the crystal lattice, how does that change the diffusion coefficient?
Well,
Yeah, there's a paper by Gunther that came out, I think 2013, which was an incredibly well done piece of scientific work. And I would call it was done by the Diffusion All-Star team. If you look at some of the leading authors, leading scientists that have been publishing in this field over the last decade, many of them collaborated on that paper. And just look at it, you see how a diffusion study is supposed to be done, where they really carefully measured every parameter. They looked at the amount of uranium and thorium content. They looked at the damage and everything, and they came up with a fairly consistent model that was quite interesting. And it showed that if you look at the range of radiation damages in a zircon crystal from very low to very high, what they showed is that you see high diffusivity at both ends of the spectrum, at the very low damage range and also at the very high damage range. There is a pretty broad range in the middle where the diffusivity is low and relatively constant. And they interpret that as a twofold mechanism. Basically, their interpretation is if you have a perfect undamaged zircon lattice, the diffusivity would be very high. As it accumulates radiation damage, the radiation damage, think of it like potholes in a street. You start blocking channels, you start blocking pathways. Atoms are displaced from the normal crystal lattice, and there's no longer these clear pathways. They coined a term tortuosity, which means that the pathway to move through the crystal becomes more twisted, more contorted, and things slow down. So once you get past a minimum damage threshold, then the diffusivity drops and it's relatively stable up until you start accumulating more and more damage. Past a certain point, you start going into a regime called a metamit crystal, which means imagine that every time you have a nuclear decay event, that there's a zone of damage. And most nucleus, and it just creates this, yeah, think of it like a truck slowly backing into your house. It just creates a big region of damage. Those regions of damage would act as traps for the helium. But as you start accumulating more and more damage, they start to merge and coalesce. And when you reach a certain point where pretty much the entire crystal lattice has been disrupted, then the helium starts diffusing very rapidly. And it goes up quite quickly with additional damage. And that is where was the regime where the Russian samples came from. They were metamix samples. They were very, very heavily damaged. If you look at where the rate samples came from, as best we can tell, of course, the Q0 was not accurately measured, and that would be one of the important things to know. But if you look at where those samples came from, they more likely were on the lower part of the damage curve, where the diffusivity would be relatively stable, but getting close to the point where it starts to increase.
Would fission tracking have the actual fission track? Would that have any bearing on the helium diffusion rate?
Well, yeah, things like that as well. Yeah, absolutely. Yeah, a fission track will create a nice pathway. Yeah.
Okay. Yeah,
and this is going down. I won't get too much into this multi-domain diffusion, but that's the entire rationale behind those kind of models, saying you can have multiple pathways, multiple mechanisms of diffusion, and they don't all behave the same.
And that would be
can't just treat
a multiple domain versus single domain diffusion model.
Mm-hmm. Yeah. Okay. And so any helium that happened to get into that fission track could diffuse quickly, but not every helium atom in the crystal would necessarily come across it. So some helium atoms would diffuse quickly, others would diffuse slowly. And if you just see a few atoms leaving quickly at low temperature and assume, well, all the atoms can leave at that temperature because we're seeing some being emitted at low temperature, that ignores the possibility that others have a more difficult pathway out of the crystal.
Let me ask you, General Han Solo, are you with us? I know you're AFK, but and listening. Did you want to add anything to this if you were still there, General? And also from the live audience, if you want any questions, please ask now. We will have an after show. I know Dr. Henke said he can stick around. Dr. Loechelt, are you able to maybe stay for a few during an after show where people can actually come in and ask more direct questions to you about this?
Yes, I could say for a little bit. I'll probably take a very short break between the two shows, but I'll join the after show.
Usually we do it about 20 minutes after so people can kind of
okay.
take a breather.
A transition time. That sounds good.
Yes. So let me see if anybody in the live chat has questions. There is a time delay, so that will take about a minute to get to them. And then General Han Solo, I don't think he's back yet, but he had some questions as well. I was talking to him earlier. He has read up on this topic quite extensively, and it's one of his personal interest topics. So that's why I invited him. So let's see if there's got any questions. Did you guys have anything you else want to add that wasn't in your presentation you might want to incorporate in this video? Because I do think this is going to be a very go-to video for this particular topic. I don't know of any video out there that has discussed this topic in this kind of depth, and I'm very grateful for it. I think this is something that has been long overdue because this is such a technical topic that when somebody brings it up, they're usually just bringing it up from what they've heard. I don't think they have the technical expertise to really dive into it, and they just say, okay, this is the claim being made, and then they throw up a page from the rate study or something. And I think that now people can actually go to this video and get a proper refutation of it rather than trying to parse through what you have written on Talk Origins, which is excellent, but for the average person, very difficult to kind of to go through and get a rebuttal from. Agreed?
Yeah, it is a very complicated topic, certainly, yes.
RSC in the live chat has asked, what are they working on? And briefly, I did before you came in, Dr. Loechelt explained your bio and how you work specifically with semiconductors and diffusion models. So do you really want to kind of reiterate on that, your expertise and qualifications on this?
Yeah. So professionally, I don't work with helium diffusion in zircon. I work more with boron, phosphorus, and arsenic diffusion in silicon. And that is, if you're familiar at all with how the semiconductor industry manufactures its devices, the process involves incorporating atoms. It's actually very similar. For instance, to incorporate boron, let's say, into silicon to change its conductivity, we'll use a process called ion implantation, which means we'll accelerate boron atoms and shoot them into the crystal lattice, and they'll penetrate to a certain depth and create damage all around it. Okay, that's just, conceptually, that's just like an alpha decay in a crystal. And now you have an atom that's been just shot into a crystal, you have damage around it, and now you subject it to heat. And the question is, where will all these atoms end up after everything is said and done? After some of that damage anneals out, perhaps at higher temperatures. And it's important for the device design to make sure that you have the boron where you want it, the phosphorus where you want it, that things are in the right concentrations. Everything has to be in the right place in the right amounts for the device to work. And the method of manufacture involves primarily using the ion implantation, which means you're just shooting in these atoms, and then annealing. So it's implant and anneal, implant and anneal. And if you look at a typical recipe for a semiconductor technology, you have implants, anneals, and then you also have some films and etch work. But that really is the heart of the manufacturing. So I'm working sort of routinely in the space of, you implant a crystal and you look at the diffusion afterwards, and you try and predict where things end up, because we want to be able to design devices, and things have to be to a certain specification. And if the boron or the phosphorus goes someplace where we don't want it to, you have leakage, you have breakdown issues, all sorts of bad things can happen. So there's a real vested interest in the entire industry to understanding these solid state phenomena. And when I saw the rate study, I thought, gee, this is right down my alley. This is something so familiar to what I've seen throughout my career. Granted, it's a different diffusing species. It's a different base crystal. but the fundamental principles, the fundamental physics do not change.
And next week you will be doing a presentation of this, and I've seen it, and it's most excellent. It is technical, not going to front, but I think that it really dives into the crux of this whole claim, this whole helium diffusion rate claim. So I'm really looking forward to that, and I know everybody else is extremely looking forward to that. So far in the live chat, I don't know if you've been following it, but it's all been very overwhelmingly positive. Although, again, certain people are having a difficult time with the subject, and don't feel bad. It's not easy. This is not an easy subject by any means. And when we do the after show, we'll kind of break it down a little bit more, hopefully, and get to a more basal level, because we understand that a lot of people have not had the prerequisite studies in either geology or physics, especially nuclear physics and mathematics, to really absorb this particular topic. And I want everybody to understand this topic. I really love doing the presentation on polonium halos, which I have on my channel. And this is like a step up from that. So quite a few steps up, probably. So it is something I have a great interest in, even though I have a very tertiary level of understanding of it. So, Dr. Henke, do you want to wrap this up for us? And then I think we'll do the after show in probably about maybe a half hour from now, which would be 4 o'clock Pacific time, 7 o'clock Eastern. I think that gives everybody time to kind of to freshen up a little bit and kind of maybe incorporate some of the information we've already provided for them.
Well, thank you very much, Steve and Gary, for this time together, and Steve, for giving me an opportunity to share on this. This is indeed a very complicated topic, and I hope that the audience got something out of it. Again, I will be responding to Dr. Humphrey's comments in the upcoming weeks, and I certainly hope that it'll be positive and constructive and specific, and that unanswered questions will be finally answered after 12 years. So thank you very much again.
Thank you very much, and I do hope the same. Dr. Humphreys has been very cordial in his correspondence. He does seem to be very willing to address the points that both you gentlemen have made, and when he does so, after he views this video, I will post them unedited on the Great Debate Community webpage, and then allow people to go there and discuss it, and allow you to read it in its entirety, and then address it in a future video. So I want to thank Dr. Humphreys for that. And if anybody else from the rate study as well wants to put forth their side, we are more than willing to either post what their refutations are, or the rebuttals, or even have them on. Dr. Baumgartner, Dr. Snelling, Dr. Austin, any of them can join us at any time. The offer has been extended to them from day one. We have a policy with the Great Debate Community. If we discuss a topic and a person is directly involved in that topic, they have a right to come in and defend their point of view on it. And I think that's only fair. So I thank you both, you gentlemen, for your time on this. This has been an excellent presentations. I want to thank Dr. Loechelt for joining us, and Dr. Henke for joining us. Sorry, Dr. Should be General Han Solo. He's not a doctor, but General Han Solo didn't get a chance to be a part of this, but hopefully in the after show he will come join. So if you're interested in the after show, it'll be about a half hour. It'll be on this channel, and I will put out the link in the Great Debate Community on Twitter and Facebook. So I ask everybody, if you like this video, please thumbs up it, share on Twitter, share on Facebook, share on StumbleUpon, share on G+. Get it out there, because it has such an incredible amount of information that I just don't think you're going to find anywhere else to be digested in this particular way. So with that, I'm going to end this, and we'll see you guys in about a half hour. Thank you guys very much.
Okay.
Thank you.
Thank you.